So in the previous two lessons, we considered the electric field due to point charges. But often we must consider a continuous charge distribution. So that is where the charge has been continuously distributed over some surface or some volume or along some line. And whenever this happens, what we must do is we break it up into smaller elements. So if we first start off with some continuous distribution, and what we do is we break it down into smaller charge elements, which is given by dq. So now what we have is an electric field due to each of these smaller charge elements, which will be given by dE 1 over 4 pi epsilon, which is a constant, by dq, so r prime to be squared, and by the unit vector. Okay, so what we do is we break it down, and then now what it becomes is it becomes an integral. Okay, so we've got the charge distributed evenly over some space, and what we must do then is to sum the total contribution together. So it becomes an integral. So the total electric field will be then given by 1 over 4 pi epsilon naught by our integral of 1 over r minus r prime to be squared by our unit vector dq. Okay, so that's our continuous distribution. Now, of course, we can have different types of distribution. We could have, for example, we could have a line charge. Okay, so here we have the charge has been distributed over some line charge, which is given by lambda. And what we do is we just break this line up into infinitesimal displacement elements, which is given by dl prime. And we can write the electric field now for this one as, again, we got 1 over 4 pi epsilon naught. And now what we have is the integral along this line charge, which is going to be given by lambda or prime over r minus r prime to be squared by the unit vector, which is given by, again, which is just r minus r prime or r minus r prime, and we integrate this with respect to the line, so we have dl prime. And the prime is very important, and I'm going to come back to that in just a little while. But essentially it says that the direction is dependent on the source, okay? And we won't be able to take this outside the integral because it's changing unless we convert it, to example, to Cartesian coordinates. So we can also have a continuous charge distribution. And for continuous charge distribution, it would be given by sigma. So again, it's something similar. We just split it up into smaller area elements. And our electric field then can be calculated. Well, 4 pi epsilon naught. Here we're doing our surface integral. And we have some surface charge sigma. Okay, which depends on r prime. To be squared, our unit vector. And it is over our infinitesimal area element, dA prime. Okay, again, the integration is respect to the prime, okay, because the direction is going to be changing depending on where your location is. Now finally, for the continuous charge distributions, we can have a volume charge. Again, we just split it up into our infinitesimal volume elements, d tau, which is given here, and we just write the electric field as one over 4 pi epsilon naught. We do our volume integral. Here we have rho of r prime over r minus r prime to be squared. And we have the unit vector. And the integral now is over an infinitesimal volume element, which is given by d tau prime. Now, it is crucial to remember that the integration is with respect to the source position, because the direction is going to be changing. Now what that means is you cannot take this outside the integral. And if you want to take it outside the integral, what you must do is convert it into a Cartesian coordinate system. Okay, so now what we can write is, we can write dq, which essentially goes to for our line element, be lambda dl prime, which will go to our surface charge, so be sigma dA prime, and then for our volume it will be rho d tau prime.